Hey guys, how we doing? We good?
Yes.
While we're waiting, any complaints about the test other than the length?
The atomic weight for I think it was nickel. Like you actually put 0.96 instead of 69.
Ah, okay.
That was it though, because I was looking at my periodic table and what you put. I
Bad
was
boy,
like, wait,
bad boy. Sorry.
it's all good.
Did I flog myself sufficiently for you, Rebecca?
Yes, I guess. I don't know.
I'm sorry.
Can I ask you a quick question?
Sure, I'll answer anything.
So I've been doing my lab manual, but I feel like I'm probably writing too much. Are we allowed to use like shorthand when we're
Yes.
writing our?
Yes. As long as I can understand it. If you make it too shorthand and I can't understand it, then no.
Okay, all right, thank you.
No problem, Dylan. Anything else, guys? Did you all see the tests?
Yes.
All right. Basically, I think the average was a 73, I want to say. 73. So basically, how that works for the extra credit is that that means it's about 2%. I would need to add to get to an average of 75. So basically, that 2% of the 125 points works out to be about 3 points, guys. Okay. And I will get that out to you soon. I'm dealing with something else. I will try and get that out tonight. It won't be that drastic a thing, okay? I mean, we're talking 3 points. How much is that going to help or hurt you? Anything else, guys? I really don't have anything to say. I think you all did pretty well, if I remember correctly. I'm not seeing anybody in this group of 6 or group of 5 that I'm not seeing anybody in a group of 5 that really did bad. Oh, by the way, I do want to show you one thing. How'd you like that last question? Ooh, I'm getting silence here. How'd you like that last question? Horrible, wasn't it? Wasn't that last question absolutely horrible? I can't believe he would put something like that in a test. Absolutely horrible. Why did he do that?
Evil.
Yes, it was an evil question. Except if we go down here to problems 3, where I said if this is really hard, look at that question, guys. This is the real evil part. The evil part is not that I put it on the test. The real evil part is that I included a very similar problem within the forum questions. Now, Rebecca, do you want to flog me harder?
Not it.
All right. Even worse, guys. If you look, you scroll all the way down here. Looky there. I even solved it for you. Don't neglect the forum questions, is I guess what I'm trying to say. Was anything blatantly unfair, guys?
No, it's actually easier than I expected.
Okay. Now the pitchforks are going after you, Rebecca. They're ready
I
to
honestly
talk.
expected it to be like longer or something.
I cut some stuff out of it. I really did cut a lot of the repetition out of it. Let's face it, I could have asked a whole bunch of questions on how many electrons, protons, or neutrons. I think my original,
Thought was gonna be on it.
what, Rebecca?
That's what I thought was going to be like more on it.
My introductory class was like that. I think yours was about 30, I want to say about 38 questions. Theirs was 51. But the reason I asked them more questions is they're more prone to screw something up. So if I give them more opportunities, then chances are they'll get it right at least 1 out of 2 times. Does that make sense?
Yeah.
Anyway, that was my thought there. Do we have anything else, guys? Anything else? The labs are going okay?
Yeah.
All right. In that case, we'll get started.
Oh, wait. I do have a question. Can you pull up the actual test questions?
Now that I'm out of this, Rebecca, you could have asked me when I was in the other screen. Okay, second step. Yeah. Okay. You seeing the screen, Rebecca?
Yes.
Okay. If it's the question about 33 and 35, those were the same exact question. So what I did was
No,
I combined the point value.
balancing one of the equations, I got really confused and for some reason I just couldn't do it. Add chlorine in it and oxygen, I believe. I don't quite remember, but it was a balancing equation.
Okay, I'm gonna try and find yours. Do you mind if I show yours test,
I don't-
Rebecca?
No.
All right.
Was it the combustion reaction one?
I
No,
think
that's
so.
there's the combustion reaction one.
Oh.
Dylan, while I've got this up, do you have questions on it?
No, I was just trying to figure out which one we were talking about.
This is the second one, the single replacement one. Is this the one? Rebecca. I see what you did.
I think so.
Yeah, that's the
Yeah.
one. It's got the chlorine in it.
Yeah.
Okay. What's the charge? Again, sometimes, guys, you got to use the test. If you are at a total loss on what the charge on something is, use the test. I told you that the reactants were always going to be balanced. So, Rebecca,
Yeah.
what's the charge on sodium?
1 second. It's either one or 2.
Are you seeing my? I'm not even sure. Am I? Are you guys even seeing me?
Yes.
You're seeing me? Okay.
It is 2. Right?
Yeah. Where am I at now? Okay. Rebecca, what's the charge? Charge on sodium?
It is 1. Yeah. Oh, it's actually 1. Yeah.
Okay. So if sodium is 1, then what is? Oh, I'm sorry. I'm sitting here. I'm trying. I've gotten. I know what I'm doing wrong. There we go. If sodium is 1, right?
Mhm.
The rest of that NaOH has to be the anion, right, Rebecca?
Yeah.
So if sodium's +1, what's the charge on OH?
+1 or -1.
-1. Keep that in mind. Now we have copper Cl2, right?
Mm-hmm.
What's the charge on each chlorine?
-1.
How many of them do we have?
2.
So what's the charge on the copper?
2.
So when you're going to write your formula of CuOH, copper has a +2 charge, OH has a -1 charge. How many OHs do you need?
Oh, so it'd be OH2.
And once
then-
it's OH2, all you got to do is put a 2 in front of the NaOH and a 2 in front of the NaCl, and you're cool.
Gotcha. Okay, I see my mistake.
Okay, anybody else have anything else? I can answer anything on the questions,
I have
on
a
the
question.
test.
We get points off for not writing solids in equations.
Yep.
Dang it.
Sorry, Joseph. I specifically, when I went through the net ionic and ionic, I specifically told you there are 4 things that you need to define an ion with: quantity, symbol, charge, and state of matter. And I emphasized that on more than one occasion, Joseph. Sorry. It's still,
Okay.
he still hasn't forgiven me, but
No, I said you're good.
okay. Anything else, guys? Okay, we got a few more people in here. I got to see who's here. I got 8 peoples. Okay, I got Arthur is in here too now. Hopefully he'll be in here soon. Okay. All right, guys, we're getting into stoichiometry. Now today's lesson is going to be, again, fairly much review. But when we get into Tuesdays, we are going to be getting into some funky stuff. I got as far as limiting reagents with my morning class. I'm really going to emphasize on Tuesday limiting reagent and quantity of excess reagent left. Now, when you guys are going through introductory, did you have to deal with quantity of the excess reagent left over?
No, I didn't.
Okay, anybody else? I specifically leave it off my intro class because intro students generally have enough to worry about to begin with without throwing this extra thing on them. I figure I can catch up in Chem 1. All right, guys. You see the screen? Screen good, guys?
Yeah.
Okay, so basically what I got to do is I got to do some review because we need some stuff before we can do stoichiometry. And that is a slight review of reactions and a slight review of moles. What we're going to do is we're going to determine the amounts produced or consumed in a reaction. We're going to get into limiting reagent and excess reagent. And finally, we're going to get into percent yield. Now, basically, you know a chemical reaction takes place if the stuff you get after mixing has different properties than the stuff you had before. For example, if you take potassium thiocyanate, a clear solution, and you mix iron nitrate, which is a slight yellowish solution. If you mix those two together, you make a blood red color. Didn't have red before, it has red now. Something must have happened to change the properties of one of the chemicals. You had a chemical reaction. Or if you take something like lead nitrate and you take something like sodium chloride, both of them are clear solutions. You mix them together. What happens is the lead reacts with the chlorine and develops a property where it's insoluble in water. So a solid develops. I have a new property. The new property is this new stuff doesn't dissolve in water where the old stuff did. Chemical reaction. If your reactants don't have bubbles in them, but your products do, that means you must be generating some kind of a gas. You could generate heat or you could have a flame produced. Has anybody ever seen magnesium being lit?
Yeah, it's like a green flame, isn't it?
Nah, it's so bright you can't really tell what it is, David. It's so bright, it's kind of like looking at an acetylene torch. It's that bright. If you actually stare at it, it can hurt your vision. As a matter of fact, whenever those happen, I refuse to look at it directly anymore because of the fact it hurts my eyes so much. In any case, what happens is you're showing that energy has been dissipated. If energy has been dissipated, there's a chance you've got a chemical reaction going on. Are we good with this? Just a slight review. Now, what happens is a chemical reaction, we rearrange the atoms. But because of Lavoisier, we don't create any more atoms or we don't destroy any atoms in a chemical reaction. In other words, the number of atoms on the left side of the arrow are going to be the same as the number on the right side in a balanced chemical equation. There you go, Joe. There are your states. You have to be aware of some of the physical states that are going on in reactions. Now, what we're going to do is we're going to see how a balanced chemical reaction has a relationship, determines relationship of reactant to reactant, product to product, reactant to product, and product back to reactant. They're all interrelated because we have a balanced chemical equation. Again, we're going to do limiting reagents, learning how much excess reagents left, and we're going to do percent theoretical yield. And the way we're going to do this is we're going to use two different things we've learned before. We're going to use the balancing of the chemical equations, and we're going to also use the concept of moles. Now, if I have a chemical equation, if I have this simple chemical equation where I have two COs plus an O2 yielding two CO2s, if I'm looking at this on a molecular level, what I'm seeing here is I have two carbon monoxide molecules reacting with one oxygen molecule to produce two carbon dioxide molecules. That's what's happening in this. That's the description my chemical reaction, my balanced chemical reaction is telling me. It's like cooking, guys. This is our recipe. If we're chemists, we are looking at the chemical reaction and we are seeing our recipe. I have a great recipe. I take 4 cups of flour, 3 cups of apples. I throw in a cup of sugar and I got some spice. I'm not going to tell you my secret on my spices, guys. I got 1/10 of a cup of spices I throw in there. I throw all that stuff together. I mix it all up, put it in an oven, and I get 14 fat. Those are actually fantastic apple tarts. Okay? I mix all that stuff together, put it in the oven, and I get 14 apple tarts. Chemistry is just the same thing. In order to make my apple tarts, I need 4 cups of flour, 3 cups of apples, a cup of sugar, and 1/10 of a cup of spices. I need all that stuff to make my apple tarts. If I need 28 of them, I'm going to need more stuff. I'll need 8 cups of flour, 6 cups of apples, 2 cups of sugar, and 0.2 cups of spices. You guys have all, is there anybody that has not baked or cooked something and followed a recipe of some type or other? You guys have done all this before. This is nothing new. In chemistry, we don't use cups. Instead of cups, we use moles. Getting back to my original equation, if I have 2 molecules reacting with 1 molecule to make 2 molecules, let me put this on the molar level, okay? If I multiply this all by Avogadro's number, and I now can look at my equation, and every time you guys look at a chemical equation, if you don't say silently to yourself what it means, you should at least be thinking of it. What this chemical reaction is really telling me is I have 2 moles of carbon monoxide. 2 moles of carbon monoxide react with 1 mole of oxygen, and it makes 2 moles of carbon dioxide. Every time you have a chemical reaction, you should be able to look at it, a balanced chemical reaction. You should be able to look at it and know in your head that this is true in fact. Now, what did we say the subscript stood for in the empirical formula? Anybody remember?
The number of atoms.
Number of atoms. Or how do we, Dylan, how do we get that? How do we get the empirical formula? Did we take the weights
Molecular weight.
and divide it by the molecular weight to get the moles? So in effect, it stands for the molar ratio of each atom in the molecule. In calcium phosphate, if I have a mole of calcium phosphate, I have 3 moles of calcium, 2 moles of phosphorus, and 8 moles of oxygen. Says so right there. Must be right. Now, if I'm dealing with a chemical equation, the coefficients in front of the molecules stand for the molar ratio between the compounds. For the reaction you see before you to go forward in its entirety, I need 2 moles of sodium phosphate. That reacts with 3 moles of calcium chloride. When that's all said and done, I end up with 6 moles of sodium chloride and 1 mole of calcium phosphate. Note, guys, I said it during the empirical formula. I'm going to reiterate it again. If you are doing an empirical formula calculation, you are trying to get the molar ratio of the atoms. Use the atomic mass of the element. We're doing stoichiometry. We're dealing with the ratio between molecules. So when we're doing stoichiometry, for the diatomic molecules, use the molecular mass. If we're dealing with oxygen, when an empirical formula, we're going to use 16. If we're doing a calculation using oxygen in stoichiometric, I'm using 32. Now, remember, I'm relating one set of moles to another, right? I got 2 moles of sodium phosphate with 3 moles of calcium chloride, right? Anywhere, am I saying anything about the relationship of grams to grams?
No.
No.
So if I'm not relating, if I can't relate grams to grams, what I can do is I have a way of relating moles to moles. So I'm going to go around, I'm going to do an end around here. In football, if the defense is really clogging up the middle, I'm going to use a little trickery and I'm going to use an end around to try and get past the line of scrimmage. So I can't go directly from mass of A to mass of C. But what I can do is I can take my mass of A and make moles of A out of that. Simple enough process. I have the formula, I know the molecular weight. If I have the mass of A, I can divide it by the molecular weight. I'm going to get my moles. Now, guys, you get to become alchemists because you get to turn moles of one thing into moles of another. And you can do that using the coefficients. The coefficients are your molar ratio. So you're going to take your moles of A, you're going to multiply it by the coefficient in front of what you want. divided by the coefficient of what you have the moles of. That will get you your moles of unknown. Then, simply speaking, if I have my moles of unknown and I want the mass, all I got to do, I have the formula, figure out the molecular mass, multiply it by my number of moles, I get the mass. Three-step process as a general rule, three-step process. Turn your known into moles. Turn your moles of your known into moles of your unknown using the molar ratio. Then take your moles of your unknown, turn it into your grams by using the molecular weight of your unknown. Simple enough, guys? Yay, nay?
I mean, I'd like to see an example, honestly, but
Oh, you're going to see examples. Okay, basically, if we're going from ground zero, though, the first thing you got to do when you're analyzing these problems, figure out what you're given and what you want to determine. You're going to have to write the chemical equation, electronically balance all the products, then balance the whole entire chemical equation. Write down the given amounts, masses, moles, volume for each reactant and or product. Determine the moles of given. Then you're going to look at the balanced chemical reaction and using the ratio of the coefficients to determine the number of moles of the unknown. Then simply you do the mass of the unknown quantity using the molecular mass. Simply turn the moles of known and turn the known grams into moles by dividing by the molecular weight. Turn the moles of known into moles of unknown using the molar ratio. Then turn the moles of unknown into unknown grams by multiplying by the molecular weight. Three-step process. You keep this down, you're not going to have any worries about these calculations. Who was asking for a problem?
it was me, David.
Hi, David.
Hi.
We have a problem here. We have a balanced chemical equation, so the first three steps of my thing are gone. As a matter of fact, do I have to even calculate moles of my starting product, David?
No.
It's given. Moles
Right.
are given. So now, David, look at the equation.
Hmm.
What am I relating to what?
I don't know what you mean by that. What are you relating?
What's the question asking me to relate?
Oh, it's asking how many moles of the hydrogen phosphate are
Phosphoric
required to
acid.
make 2.5 moles of the water.
So I'm relating water.
The water to the
Phosphoric
sodium
acid.
phosphate or hydrogen
Okay.
phosphate, yeah.
All right. I'm relating. Is the water a product or a reactant?
It's a reactant. Or product, I'm sorry.
And the phosphoric acid is?
Is the reactant.
So basically, I'm using what I have to relate a product back to a reactant. Okay? I have basically the first step of my problem done because we've already turned our H2O into moles. Correct, guys?
Mm-hmm.
So I am needing to change my moles of H2O into moles of phosphate. Do I have a relationship between water and phosphoric acid? David?
Well, you have both of the moles of each.
Nope, I only have the moles of my H2O.
Oh. Well, you have it in the original equation though, right?
I have it in the original equation. If I have 2 moles of phosphoric acid, how many moles of H2O do I have?
3.
So I have the relationship between the two for this equation. We know how many moles of H2O we have, and we also know the conversion between the H2O and the phosphoric acid. So I have 2.5 moles formed, and from the equation, I know that the molar ratio is 3 H2O to 2 phosphoric acid. So all I got to do is use that ratio for me. I'm going to, again, guys, I know it's a pain in the butt to use labels, but labels will prevent you from multiplying when you should divide and dividing when you should multiply. So when I'm doing this, I have 2.50 moles of H2O. I know my moles of H2O are going to go on the bottom because I want to cancel it out. So the coefficient in front of the H2O is 3. I put my phosphoric acid above that, put the 2 right beside that. So I have to multiply my 2.50 by 2/3. This gives me 1.67 moles of phosphoric acid can be formed from 2.5 moles of H2O. Now, if I want the grams of phosphoric acid, all I got to do is figure out the molecular weight, which is 98 grams per mole. And I simply take my moles and multiply it by grams of phosphoric acid over 1 mole. I have 163 grams of phosphoric acid. Questions on
To
this?
set it up as one equation.
Dylan?
Will we be allowed to set it up as one equation
Yes.
instead of 2 separate?
Yes,
Okay,
Dylan.
thank you.
I don't care. Dylan, from my logic, my perspective, it's easier for me to see things step by step. If it's easier for you to see them with the long process, please do it. Okay?
Okay. Thank
Dylan, good for you. How many grams of sodium phosphate would be formed if I have 171.5 grams of phosphoric acid? Again, I'll ask you the same question I asked David. H3PO4, is it a reactant or a product?
The H3PO
H3PO4,
will be
reactant. So in this particular problem, okay, the Na3PO4, reactant or product?
Product.
Product. So in my first equation, I was relating a product back to how much reactant it took to make that form. In this case, I'm telling you how much of the reactant I have, and I want to know how much product is formed. So in this case, I'm relating a reactant back to a product. Again, 3-step process. Find moles of my known, use the molar ratio to find the moles of my unknown, then multiply by the molecular weight to get the grams of my unknown. Dylan, what is my known here?
the grams of H3PO.
Okay, I got to turn that into moles. What am I going to do, Dylan?
Divided by the molar weight of H3PO.
And that is 98, roughly speaking. So I'm going to take that and divide it by 98. And lo and behold, I get 1.750 moles of phosphoric acid. Now, Dylan, what is the relationship between sodium phosphate and phosphoric acid?
For every 2 moles of Na3PO4, there's 2 moles of H3PO.
So I'm going to use that relationship. And I got 2/2. Amazingly enough, if I start out with 1.75 moles of phosphoric acid, I'm going to make 1.75 moles of sodium phosphate. Now, finish it up for me, Dylan. I got moles of sodium phosphate. I want to know how many grams of it I have. What do I do now?
Multiply it by the molecular weight.
I'm going to figure out what the molecular weight of the sodium phosphate is, which is 163 something. And I'm going to multiply that by the number of moles I had. And lo and behold, I have the grams of sodium phosphate. Questions, guys? Questions? Anything?
Nope. I'm good.
Seems good?
Mm-hmm.
Okay. All right. Now, another problem. I have phosphoric acid. How many grams would be completely reacted with 162.5 grams of sodium carbonate? Jackson, you're around.
Yes, sir.
Jackson, phosphoric acid, is that a reactant or a product?
That's a reactant.
And the sodium carbonate?
That is a reactant as well.
So, Jackson, I've been relating reactants with products. Can I relate a reactant with another reactant?
Yes, I forget how.
Not directly.
Well, you can, you just threw me there. What do you mean by not directly?
Because you'd have to compare it to a product, and then therefore with the product value, compare it with the reactant again.
No, you don't, David. No. That's the beauty of this. That's the beauty of this whole system. You see, just like 2 moles of phosphoric acid made 2 moles of sodium phosphate, David, if I've got 2 moles of phosphoric acid, that's got to react with 3 moles of sodium carbonate. So I can relate one reactant directly with another one. The same way I just did it. Okay?
You can compare them with any molecule within the equation.
Absolutely. Absolutely. That's because we know, because of our coefficients, we know the molar relationship between all of the reactants with all of the products. So David, you've already done one of these, haven't you?
Yeah.
Okay, Jackson, keep on with me, okay?
Yeah.
All right, what's the first step behind doing this problem?
Yeah, so it gives you grams of the NH2CO3.
So what
Convert
are you
that to
gonna
moles.
convert it to moles using the molecular weight? So sodium carbonate happens to weigh 106 grams. I divide that into 162. I get 1.533 moles of sodium carbonate. Now, Jackson, I want to
Okay.
know how many moles of phosphoric acid.
So
What
you
am
look
I
in
going
the
to multiply
chemical
by?
equation. There is the 3 moles of NH2CO3 and 2 moles of the phosphoric acid.
So am I doing 2 over 3 or 3 over 2?
2 over 3.
2 over 3, because I want to cancel out moles of sodium carbonate. So the 3 goes on the bottom, 2 goes on the top. So if I have 1.533 moles of sodium carbonate, I need 2/3 of that in phosphoric acid. So I need 1.022 moles. Finish me up, Jackson.
Then you need to find the molecular mass, which I think you've given 98 grams. I think that's what it is.
Very good. So if I have 1.022 moles, I end up with 100.2 grams of phosphoric acid. Any questions here?
No.
Okay. Anybody know what the products of a bicarbonate reaction with an acid are? Okay. Does this look like an acid-base reaction?
Yes, because of the hydrogen.
It looks like an acid, but you're not really too sure about this carbonate business, are you?
Mhm.
So we act this like a double replacement reaction, okay? If this is a double replacement reaction, what goes together? Do the easy one first. What can you identify as a cation in the second compound?
The carbonate?
No, carbonate is not a cation.
Potassium.
Potassium. Potassium's a cation. Everything else, when you have a metal The metal's the cation. Everything else in the formula is going to be your anion. So if potassium is my cation in my second atom, what is the potassium fixed up with?
That's so four.
Sulfate.
The sulfate. So I have one of my compounds is going to be KSO4. Okay? Now, the other two things that are hooking up are we're going to throw another hydrogen on that plus CO3. And the relationship there is going to be H2CO3. Now, that's got H2CO3 has got two very extremely stable compounds within it. CO3, can you think of a stable compound that's all real close to CO3?
Carbon dioxide.
Carbon dioxide. So if I take the carbon dioxide out of the H2CO3, I get H2s and O's, right? So
Water.
when you have a bicarbonate reaction, the products are going to be the salt, potassium sulfate, water, and CO2. Okay? So, I don't understand what happened. Okay. I went backwards is what happened. So we got our products. All right. Is this reaction balanced? Are the chemicals balanced?
No.
You're right.
No, because the potassium is a +1.
And the sulfate is a,
It's a -2.
so what do I have to do to fix that?
K2SO4.
Okay. Now, who's it? David or Dylan?
Yeah, that was David.
David, I got K2SO4. How do I fix the balancing of, everything's balanced. Chemicals are all balanced now.
Mhm.
If
need
I
to
got,
put
how
a
many?
2 in front of the potassium in the yeah, there you go.
I put a 2 in front of the potassium bicarbonate. That gives me a total of 4 H's on the left. I got to put a 2 in front of H2O. By putting the 2 in front of the potassium bicarbonate, that makes me put a 2 in front of the CO2. Amazingly enough, I got 2 high oxygens from water, and I got 4 from the CO2 for 6 O's. 2 times 3, 6 O's. We are now balanced. We now have a balanced chemical equation. Now let's go back to the original equation. David, you were saying you were worried about comparing one reactant with another reactant. Do we have reactants in this particular problem?
Yeah, we have 2 reactants.
We do? What are we
Yeah.
comparing?
Oh, for the question here. Oh, no. You're just comparing, you're changing the units on it. How many liters to,
But no, just right now, I'm asking you. I got CO2 and water. I'm trying to compare CO2 with water, right, David?
oh, okay, yeah, right.
Are they, what's CO2 in this problem? Is it a reactant or a product?
It's a product.
And water?
Is also a product.
So remember, we just related one reactant to another reactant. Here, we're relating one product to another product. Okay?
Mhm.
All right. This seems like a difficult thing to deal with because we're trying to figure out volumes when we've got grams given. But I got these nice 3 little letters over here, guys. Anybody remember what STP stands for?
Standard time pressure.
Temperature.
Oh, temperature pressure.
Okay. Now, there was a relationship between liters and moles if we were at standard temperature and pressure. Does anybody remember what that relationship was?
22.414 liters per mole.
If a gas, any gas, is at 0 degrees Celsius and 1 atmosphere pressure, and there is 1 mole of it, it will occupy 22.414 liters. So if you can get the moles of CO2 gas, you can determine the liters at STP. Okay, now let me see who I haven't bugged recently. Blake. You out there, Blake?
I am.
Good, 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 good. We have 348.2 grams of water. I want to know how many liters of CO2 gas we have. Okay, so our 3-step process. We've got a balanced chemical reaction. What's the first step of our 3-step process?
We're going to want to turn moles into
Great.
mole mass.
We're going to want to turn, we aren't given moles, Blake.
Oh, well then this is wrong.
What do we want to turn the 348.2 grams of water into?
We want to turn it into CO2.
Eventually, yes, but there's a first step we have to go to.
We don't want to turn it into moles.
Yeah, we do want to turn it into moles.
Okay.
You said turn it, you gave me an ambiguous answer.
Okay. Yeah,
So-
turn it into moles.
Turn it into moles. That's the first step. So we have 348. What's the molecular weight of water, Blake?
Isn't it like 20 something?
18.
18. Thank you.
Guys, that's one of those ones that you just gotta. Haven't you done it
It's-
enough? That's
Yeah,
like you weren't surprised that it was 18, were you, Blake?
I wasn't.
So I'm going to take my grams of water divided by 18. I now have 19.32 moles of water. Blake, what's my molar ratio between water and carbon dioxide?
Don't you just compare the atomic masses to each other?
No, Blake. No, no, no. No. Can't do that.
Way wrong.
No, Blake, stick to the process we're doing here. We have a 3-step process. First thing, you take your known, make it into moles. Okay? Second thing, you turn your moles of your known. We now know how many moles of water we have. We have to turn that into moles of CO2. Do I have a relationship between water and CO2, Blake?
Yeah.
What's that relationship? Look at the equation.
Oh, it's is it 2? 2 to 2?
2 to 2.
Ratio?
So
Oh.
if I have 19.32 moles of water, I'm going to make 19. At the same time, I will have made 19.32 moles of CO2. Now, do you remember what the relationship between liters and moles was at STP, Blake?
No.
Somebody yell it out.
212.
No. Not that. Not
22.414.
22.414 is the relationship of volume, is a relationship between liters and moles at STP. So if I have that many moles of CO2, I know the relationship is 22.414 liters per 1 mole of CO2. This is going to give me 433.1 liters of CO2. Are we good, Blake?
I mean, I've got a lot of work to do on this, but yeah, we're good on this.
Okay, just what I'm going to do is I'm going to stop this because I want to go back for a second.
And Professor, I just want to reiterate, you said that the 22.414 equation that we would use for conversions, that works with any molecule,
Any gas,
any gas.
any gas.
Okay.
Okay. Why isn't this not doing it? Why are you not doing it? Thank you. Okay. All right. Some things you have to realize. I'm going to just blurt them out right now. Okay. What you're trying to do is you're trying to get moles of your known. You can convert moles of your known into moles of your unknown. You can do that because you have a balanced chemical equation. That's the step you know. But how do we get moles of A? If we have grams of A, we simply divide it by the molecular weight, right? If we have liters of a gas at STP, we can take those liters and divide them by 22.414, and that will give us moles. So we have two tools in our pocket right now. You guys have had intro, so you have been exposed to concentrations and volumes. Do you remember molarity and liters, guys? This is in our
Yes.
future. You're going to be able to take liters, the volume of your unknown. If you have the volume and you have the concentration of the solution, you can multiply the two of them. That will give you moles. We're going to go through gases soon. Gases have the ideal gas law. PV is equal to nRT. If you know the pressure, volume, and temperature, you can get the moles of the gas that way. Those are going to be 4 tools you're going to be able to use in your belt to get moles of a known sample. This is the easy part because all you're going to do is look at the equation. Then, once you have moles of your unknown, you're going to be given information that will allow you to answer the question that's given. You may have to take the moles of your unknown. If you happen to know how many liters that solution is, then you can get the concentration of your new sample. If this is a gas and you're still at STP, you can determine the volume of this at STP. If you have the moles and you know the volume, temperature, and pressure of it, if you know the 2 of the 3 things, if you know the volume and the pressure and you know the moles, you can guess what the temperature of that is. That's where we're eventually going with this. For right now, for what you have to know right now, you have the ability to take grams to moles, moles to moles of unknown, and then moles of the unknown to grams. But the other things are coming up. Okay. I have other problems. Do we seem pretty solid? Do we seem pretty solid in our relationships here? Do we have stoichiometry fairly well down, guys?
Yep.
Okay. I've got plenty of problems that are after this. But if you look at the problems, much like I just went through, I'm going through them in a step-by-step fashion. So you should be able to follow. If you need another example, there are other examples that are given here, okay? Does anybody need me to go over any more examples? Now, the reason I was making such a big deal about whether something was a reactant or a product is because of just some of the same thing that David was having a problem with. You have to realize that if you have a balanced chemical reaction, you can relate a reactant to another reactant. You can relate a reactant to how much product you make. If you have so much product formed, or if you want so much product and you want to know how much reactant you need, you can relate the product back to the reactant. Or if you need to determine how much of a byproduct or how much of something else gets formed with the stuff you really want, you can do that by comparing one product to another product. Are we good, guys? Are we good?
Yeah.
Okay. Arthur. You've been quiet, Arthur. You're out there. Maybe too quiet. Arthur, you're out there. Okay, give me Rebecca then. Rebecca.
Yes.
Hi.
Hi.
You have to make ham sandwiches. Okay?
Okay.
You have 24 slices of ham and you have 10 slices of bread. I like to put a bunch of ham in my sandwiches. I put 4 slices of ham in each sandwich. How many sandwiches can I make?
So you have 24 slices of ham and you have 24 pieces of bread, you said?
Nope, I have 24 slices of ham. I've got 10 slices of bread. There are 4 slices of ham that go into each sandwich. How many sandwiches can I make?
6.
How much bread do I have, Rebecca?
10 slices.
So if I have 10 slices of bread, how many sandwiches can I make from those 10 slices?
Only 6, because you only have 24 pieces. Right?
Rebecca, I have 10 slices of bread.
Tell me the answer.
Rebecca,
Yes.
I have 10 slices of bread.
Oh,
How
5.
many slices
I'm
do you
sorry.
usually, how many slices do you usually use in a sandwich, Rebecca?
8 open face sandwiches.
We're not dealing with open face sandwiches. So if I have 10 slices of bread, I can make how many sandwiches?
5.
If I have 24 slices of ham and there are 4 slices of ham per sandwich, how many sandwiches can I make?
6.
But I can't make the 6. I can only make 5 because I've run out of bread, right?
Yes.
Believe it or not, Rebecca, you just used stoichiometry to figure that out. Because the coefficient in front of the ham was a 4, the coefficient in front of the slices of bread was a 2. You have used that in your calculations. All right?
Mm-hmm.
You were limited by the fact you didn't have enough bread. Okay, let me ask you another question, Rebecca.
Okay.
How many slices of ham are left over? You made how many sandwiches, Rebecca?
5. So 4 slices of ham.
You had 5 sandwiches. Each one of those sandwiches had 4 slices of bread. So you used 20 slices of ham. You started with 24. You have 4 slices left. That is how you calculate the amount of excess stuff left over. We also were able to calculate what the limiting reagent was. Okay, thank you, Rebecca. Let's go back to my original equation, my original fats, my original fantastic apple tarts. Arthur, are you there yet? Okay, who haven't I picked on recently? Min. Are you there, Min? Okay. Joe, I haven't talked to you for a while. Joe.
Yeah, I'm here.
Yeah, I'm here. Like you really wanted to be called on. Okay, Joe. This is my recipe. 4 cups of flour, 3 cups of apples, 1 cup of sugar, and 1/10 of a cup of spices. What happens if I go to my pantry and I've only got 2 cups of flour? Can I make 14 apple tarts?
No.
What's the maximum I could make?
Wouldn't it be like half?
I'd only be able to make 7 of them. So what's extra, Joe?
7.
No, 7 is how many I made. The flour is my limiting reagent, right? If I have
Okay.
4 cups of flour, I need to use up 3 cups of apples. But I need to use up 3 cups of apples. But I only had half of the flour. So how many apples did I use up?
1.5.
So I used up 1.5 and I have how many left?
1.5.
My sugar.
0.5.
How much did I use up?
Half. It's like 0.5.
And how much is left?
0.5.
You see where I'm going with this?
Correct.
So the first thing we have to do is we have to recognize you need to recognize a limiting reaction problem. Okay? Bottom line, we're going to be limited by something. Something's going to run out. When it runs out, reaction's dead. So we have to be able to recognize how we determine a limited reactant. Anybody know how you do that? I can tell right off the bat, I can tell this is a limiting reagent problem. How did I do that?
One will have less than.
One's always going to have less unless it's exactly perfectly measured out. So if one's always going to have less, Dylan, how do I know right off the bat this is going to be a limiting reagent problem? How many amounts am I given?
2.
If I'm given 2 amounts, one is going to run out before the other, right?
Right.
So if you're looking at a problem and you see 2 amounts given of reactants, if you have 2 amounts of reactants given, it's a limiting reagent problem. So how do we determine the limiting reagent? There are various ways, guys. What I'm going to do is I'm going to stick to one way. There are other ways of doing this. Just understand, I'm sticking to one way. You can use those other methods if you want. But I'm going to stick with one way to avoid confusing those that are not able to see that there's more than one way to do it. Okay? What I'm going to tell you to do, I have 2 amounts of my reactants. I'm going to tell you to pick one product and tell me how much of that product each one of those reagents is going to make. Then once you've figured out how much each one of those will make, you look at how much product was created. The one that makes the least amount of product, that came from the limiting reagent. That's the amount you report out. Does that make sense to you all?
Not really. I'd need to see it in an example.
All right. I just happen to have one. Okay. All right. I have calcium chloride and silver nitrate. I'm starting this from bare bones, guys. I got to write the reaction. Calcium chloride reacts with silver nitrate, double replacement reaction. I get calcium nitrate and silver chloride. The silver chloride is a precipitate. The reaction goes. All right. Next step, I got to balance each compound electronically. David, is my calcium chloride balanced?
Yes.
What's the charge on calcium, David?
+1.
Look again.
Oh, +2 then.
+2.
Okay.
Chlorine.
Is a -1.
So, what subscripts go?
Cl2. It needs to be Cl2. Yeah.
Silver. Anybody? Let's go with Blake. Silver nitrate. What's the charge on silver?
Is it going to be +1?
Nitrate.
-1?
Is it balanced?
It is.
Okay, we'll give you a harder one again. Calcium nitrate.
Calcium's +2.
Nitrate.
Nitrate's
You just said it a second ago.
-2?
No.
No.
You,
Oh, sorry, man. It's been a long day.
you You just told me a second ago nitrate was -1 and I agreed with you.
Yes, indeed.
Has anything changed in that 5 minutes?
No, I'm throwing to see what sticks. It's negative.
Okay, so calcium's a +2 and NO3 is a -1. Fix it.
You'd have to multiply the calcium by 2 and the NO3 by 2,
It's been a
or
long
calcium by
day.
3.
It's been a long day, Blake.
Yeah. And
Calcium is a +2, NO3 is a -1. Do you need any more calciums?
Oh, no, you don't.
You
just
need more
another.
nitrates.
Yes.
So, parentheses, little 2. Okay?
Mhm.
Silver chloride. Does anybody not agree that silver is a +1 and chlorine's a -1? So that one is balanced. Now I have everything balanced in terms of charges in this Now, are my calciums even?
Yes.
Silvers?
Yes.
How about my chlorines?
No.
What do I have to do?
You need to put a 2 in front of the silver nitrate and a 2 in front of the silver chloride.
Okay, you anticipated. Good. Now we're balanced. Now, again, we're just going to make this look like a regular stoichiometric problem. Only I've got to solve 2 problems. I've got to solve the calcium chloride to find out how much silver chloride it makes. And I got to use the silver nitrate to figure out how much silver chloride it will make. Again, same thing. We're going to change the moles. Once we get the moles, change it into silver chloride moles. And then we're going to stop for a second. Okay, if I have that many grams of calcium chloride, I divide by the molecular weight of calcium chloride, I get 0.0506 moles of calcium chloride. If I have 5.23 grams of silver nitrate, divide that by the molecular weight of silver nitrate, I get 0.0308 moles of silver nitrate. Doesn't look very fair. Who's betting right now that the silver nitrate is going to be the limiting reagent? Anybody want to bet your next quiz? And
No way.
No fair looking ahead. All right, for every 1 mole of calcium chloride, there are 2 moles of silver chloride. And for every 2 moles of silver nitrate, there are 2 moles of silver chloride created. So if I look at this, I only make, from the calcium chloride, I only make 0.101 moles of silver chloride. From the silver nitrate, I make 0.0308 moles of silver chloride. You should have taken the bet. Which one is smaller, guys?
The silver nitrate.
The,
Or you mean like atomic
yes, yeah,
size?
exactly. No, exactly.
Oh.
You answered the question I wanted, David. I produced, from the silver nitrate, I only produced 0.0308 moles of silver chloride. From the calcium chloride, I produced 0.101 moles. Now, why didn't I take it to the final thing? Why didn't I take it to the final step and make grams out of this? Don't I need to determine grams before I can figure out which one produced more or less silver chloride?
You started off with grams.
Yeah, I started off with grams of this stuff. I took it through and I figured out how many moles of silver chloride I have of each. My question was, don't I have to take it to grams to figure out which one is larger? No, guys. Because look, if I multiply this by the molecular weight of silver chloride, I'm also multiplying this by the same number. I'm lazy, guys. Once I get to this step where I found the moles of my product, I compare the moles. And if I compare the moles, I know this one is going to produce less because it's got less moles. All I got to do is then do one calculation. I'm going to take the moles of silver chloride, multiply it by, I think it's 143 point something grams per mole, and that will give me the amount that I have. I was right, 143.32. Okay, we've gone through one limiting reagent problem. We're going to go through a couple more. Anybody have any questions? We did stoichiometry tonight. Remember, three-step process. Take the grams of the known, make it into moles. Take the moles of the known, turn it into moles of unknown. Then take the moles of the unknown, multiply it by the molecular weight to get the grams of the unknown. You recognize limited reagent problems by knowing that there are two amounts of reactants. There are two reactants that have an amount of the amount of each of them. That's how you recognize something as being a limiting reagent problem. If you see two things listed in the problem, then you need to take both of them to see how much product you create. You look at the amount of product that's created. The one that created less came from the limiting reagent. That's the amount you report out. Again, I'm going to go over this on Tuesday, and this is basically where we're going to start from. Any questions before we go? Then you all have a great weekend. Don't study.
Perfect.
Take care, guys. All right.
Thank you.
Thank you.
Bye.
Bye. If anybody has anything you'd like to stay and talk to me about, I'm here. Min, do you need to talk to me about anything? Min, are you there? Okay, man. If you're there, good. You have a good weekend. If not, you're going to come back and find that we're gone. Take care.
Bye, teacher.
Take care, man.